Hello and welcome to this discussion on validity, bias, and confounding. A lot of the things that we've been talking about up until this point have really been pointing to this discussion. And so when public health professionals really start understanding how all of the pieces of biostatistics and epidemiology work together, a lot of times this is where that can really come together. So this diagram that I have here should be a familiar diagram by now. We start out with a population, and from that population we take some kind of a sample. A simple random sample is ideal because then we know that we have an equal chance of each person from that population being selected to be in our group that we will study. So then here we have our sample, and for each individual in our sample, we measure something. We might measure some exposure status. Sometimes that's a grouping variable, sometimes that's a continuous variable. We also may measure some kind of an outcome. And so what we're looking for often is whether there's some kind of a relationship between the exposure and the outcome. And ideally, this measurement that we take will be accurate. So I'll put that here. Once we've taken those measurements and we've analyzed them, then we can go back to inferring something about the population. And you'll probably remember that we measure things and we calculate things like maybe the sample mean, and then we go back and we infer the population mean. So based on these measurements that we've taken for each individual, then we can say something back about that parent population that we think that we're trying to represent. So this has everything to do with validity and bias. And so let's start off by talking a little bit about bias. The first bias that I'd like to mention is called selection bias. And this is a bias that's based on how we selected our sample. And so if we select our sample in such a way that they do not really represent this original population, then the results that we get really don't represent the whole population, they only represent a subset. So selection bias can be a problem. Now, one scenario where this can happen is something called non-response bias, and you can read about this in detail in your textbook. But essentially, non-response is where we may have tried to include somebody, but because of something that's unique about that individual, they did not end up getting to be part of the sample. Maybe we used random digit dialing to get to find our particular sample. Well, if a person does not have a telephone, then they really aren't part of they have zero chance of being part of the sample that we draw. Your textbook talks about an example where women had to have a driver's license. Well, there are some women who don't have driver's licenses, and they probably are different from those who do in certain specific ways. Usually, if we have non-response bias, we don't even know who those people are, but every once in a while we may have a situation where we can evaluate that. And so I'd encourage you to read in your textbook about non-response bias. So that's a subtype of selection bias. Now, before we move on, I want to talk a little bit about having kind of what kind of sample we get. In some of the studies that we've looked at so far this quarter, you've seen that depending on where that data came from, they were trying for something that would sort of approximate some kind of a nationally representative sample. And this really gets into who can, once we've taken this sample, who can we then infer the results back to? So if I try to draw a sample that represents everybody in the nation, then I would then be able to better infer back to everybody, say, who lives in the United States. And so a lot of times we may think of NHANES or the National Inpatient Survey as being nationally representative samples, so that then the findings that we find from our particular little sample can be inferred back to lots of people in the population. Now, we can't always get a nationally representative sample. Sometimes we're kind of stuck with smaller groups, and sometimes we even select specifically subsets of the population. And so we just need to be careful then, once we have selected that not so nationally representative sample, we need to be careful about not claiming to know about the whole population, where we can't extrapolate beyond what we have actually looked at. So if we only look at people who, say, live in California or the West Coast, or we choose a sample that is from the Southeast part of the nation, that the things that we find in those particular locations may not apply to other people. So that's why we try really hard to get this nationally representative sample. The second type of bias that I would like to talk about is called information bias. And okay, so this was selection bias, and this is information bias. And information bias, there are several different common types of information bias. And before I get into that, I want to add a couple of things to this idea that once we have a sample, we want to measure things in a way that's accurate. First of all, I want to add another term here, and that is that we also want our information to be what's called reliable. And just on the kind of the way we use the words in general, a lot of people kind of use reliable and accurate interchangeably. So I want to make a distinction specifically for epidemiology. Reliable means that my measurements are close together. So I want you to imagine that, let's say there's a scale, and you can step on it and you can weigh how much you weigh. I don't know if you've ever done that. You get on the scale and you look down and you're like, oh, wait a minute, I'll get off, and you reset the scale, and then you get back on and you're like, oh, okay, that's better. So sometimes when you use an instrument like a scale and you try to measure something, sometimes it gives you slightly different numbers. If you were to weigh yourself, say, 10 times in a row, and you're wearing the same clothes, you don't go eat lunch in between, you're just kind of like getting on and off the scale every 30 seconds, sometimes those measurements are not exactly the same, and that would be an example of this reliability. Now, if I got on a scale and it weighed me 2 times and it was off by 1/10 of a pound, that would probably be considered pretty reliable for somebody, who's like a person. That's not a big difference. But if every time I got on the scale it weighed me and it gave me a difference of, say, 10 pounds from one measurement to the other, that would not be considered to be very close together. And so this reliability really has to do with we need to know that when we measure something, that we can count on it being the same each time we measure it. Accuracy is a slightly different concept, and what this means is that it is on target. And what that means is if I weigh a certain amount, if I have a certain weight, that the scale actually weighs me at that weight. And so accurate is a slightly different thing than being reliable. A scale could weigh me at 10 pounds too light over and over and over and over and over and over again, and that would be reliable but not accurate. But if it's accurate, that means it's also the number that it gives you is correct for that particular person. And so we'll use this example of a scale. I want my measurements to be both reliable and accurate, so that when I use those measurements to infer back about the population, I know that the information that I have is correct. So let's talk about a couple of different kinds of information bias. One of them is called recall bias. And by the way, all of these are listed more in detail in your textbook, so I'd recommend that you look those up. Recall bias means that the person who is the study participant remembers things differently depending on what group they're in. Like, let's say you're studying about, we studied about hearing loss and preterm births. Let's ignore the hearing loss part, but let's say that a person has an infant who was born preterm. They tend to think and think and think and think and think about what could have happened. Was I sick with the flu? Did such and such happen? And so they may remember things differently than the mom who did not have that particular outcome. So recall bias is something that happens when the study participant remembers things differently depending on the outcome. Another kind of bias is called prevarication. That's a fancy word for lying. And sometimes the study participant doesn't mean to be dishonest or to lie, but they maybe are trying to help the study researchers, and so they tell them what they think they want to hear. And these can kind of be related. Maybe they actually do remember it more, and so they kind of beef it up a little bit. Sometimes prevarication bias can be simply they're just lying, and for whatever reason they may have. And so if they give you the wrong information, maybe you're asking about some kind of exposure and they say, yeah, that happened to me, when in actuality they know that it didn't, then that can definitely affect your study results, cause a bias. Another kind of bias is one that's actually caused by the researcher or whoever the researcher assigns to do the interviewing. We call this interviewer bias. And a lot of times when we're collecting information, we try to get that information as accurately as possible. So we might have an interviewer go and fill out the form with the study subject. And so the interviewer, if we have interviewer bias, an example of that would be that if the interviewer thinks that or knows that the person had the outcome of interest, they may ask questions differently of that particular study subject. They may probe more deeply about a specific thing to get the answer that really points to an exposure that they were kind of after. So if an interviewer asks questions differently, depending on what group that study participant is in, you may end up with interviewer bias. And another kind of information bias is measurement bias. Here we're actually measuring something, and the information can be biased if we measure things differently for the two groups. So let's go back to our example of the scale. Let's say that you have a scale in a doctor's office, and maybe this is your control group, and so everybody gets on the scale, and so they weigh themselves, and that particular scale weighs every single person 10 pounds lighter than they are, or a certain percentage lighter than they actually are. And then let's say maybe your cases all go to a different clinic, and they have a scale that actually measures much more reliably and accurately. They're on target, and so they don't weigh too light. And so those two groups would be biased from each other. They would be measured differently. And that gets us to this whole concept of whether something is, let me choose another color, differential bias versus non-differential bias. Differential bias means that for some reason, people that are in two groups have this bias applied to them differently. And if we have differential bias, then that can really affect whatever measure we're using for our study. It can decrease the effect that we see, like a relative risk or an odds ratio. It can increase the effect that we see. It can even reverse the effect so that maybe it was a positive effect and it reverses it to negative. And so it's really important when we're thinking about bias, if we're reading a particular study and we're saying, wow, that might have been affected by bias. If it's differential bias, then that's way more problematic than being non-differential bias. So let's go back to the example of a scale. Let's say that every single person uses the same scale. It's calibrated the same, whether you have people in the control group or the cases group, and it weighs everybody 10% lighter or 10 pounds lighter than they actually are. That's called non-differential bias because the bias is applied the same to everybody in the study. It's not different. Differential meaning different. So that can be a really important feature when we're thinking about any of these biases. So those are some examples of information bias. That brings us then to this whole concept of validity. Now, one way of thinking about validity, people actually, this whole concept of accuracy is synonymous with validity. And in terms of validity, what we're often referring to is both internal and external validity. And if we're thinking about internal validity, then what we're actually saying is within the people in our actual sample, the people that we studied, did we measure, did we study the things that we thought we did? This is internal validity. And so did we capture what's really true about these people that are in our sample? If we were then to think about external validity, that has to do with do our results apply back to whatever we think is our target population? So this is our external validity. External validity is synonymous with generalizability. Can we generalize our findings to more people than just the ones that were in our sample? Because if the only people we can generalize to are those 10 or 15 or 100 people that are in our particular sample, then that doesn't help us know something about somebody else that maybe wasn't part of our particular study. We want to be able to generalize our findings to more people. So that's what external validity is. And so validity has a very specific meaning in epidemiology. The last thing that I want to talk about is actually this idea of confounding. Now, we've talked quite a bit. Let me get rid of that line. We've talked quite a bit about measuring things that have to do with the exposure. A lot of times that's a grouping variable, but can be continuous. We've talked about measuring the outcome for our study, and we want to see that relationship between exposure and outcome. And something sometimes happens where there's another variable that's related to those two, and it's called a confounder. And confounder, the word actually means that it kind of, it's a mixing of the results. In other words, the confounder can be mixed in with the exposure, and those two things can be mixed up together when they have their impact on the outcome. So let's look at kind of an example of a confounder. If we were looking at the relationship, let's say, between an exposure and an outcome, let's say this maybe is a toxin and this is some kind of a disease. Not everybody who's exposed to the toxin gets the disease, only some people. And so we can calculate some kind of a relationship between the exposure and the outcome, and we call that simple relationship the Crude Relationship. And so let's say we calculate maybe a relative risk equal to 10. Now, if that particular relative risk is only due to the exposure, the toxin, and the outcome, the disease, and there's nothing else that impacts that relationship, then no matter what other variables we add, it will not change this relative risk of 10 value. So let's say we adjust for a person's sex or gender, and that becomes, say, 9.8. Well, that difference isn't very big. It's essentially the same. So we still have a relative risk approximately the same. Let's say then we maybe adjust for region of the country, something geographic. And maybe then our relative risk is 9.9. Let's say maybe we adjust for age. And age is often a very strong confounder for many relationships, but let's say in this case maybe it's 9.7. We could adjust for all three of those together. Let's say sex, geographic, age, and maybe our overall relationship there is 9.6. This really has not changed significantly. There are little bits and pieces of this relationship that have to do with sex, geography, and age, but it's not a really big difference. So, and then let's consider another example. Let's say that instead of adjusting for all of these things, we adjust for education. Now, if education is an important confounder in this relationship between exposure and outcome, a lot of times what we'll see is that relationship will change significantly. Like, let's say our relative risk then becomes 2.4. When we add education in, the relationship that we see between these two variables changes a lot. And so what that means is that variable probably is a confounder to that relationship. And so once you get into this realm of confounding and all that, there are a lot of ways that we can search for that. But the main take-home message is that if that variable causes a big change, then there definitely is something that you want to take a look at and see if there's something about education that's related to that toxin or somehow related to that disease that's really muddling or confusing or confounding the relationship that we thought we were looking at here when we were just looking at the two variables by themselves. So that concludes my talk about validity bias and confounding. Thank you so much for joining me.